Okay, hello everyone. I guess I need to introduce my mentee, Melih. So basically, once we start this DRP project, he was about to graduate. Now he indeed graduated from the Boğaziçi University. So I want to congratulate Melih again for that. And I hope a bright future for him. I mean, for all of us, obviously. And if we want to talk about the presentation, so he will talk about the integer partitions. In particular, he will talk about the Rogers-Ramanujan identities, and we'll present an attempt to find the bijective proof of the first Rogers-Ramanujan identity. Melih, the floor is yours. And also, I want to thank you and all of the DRP organizers for this thing. Thank you.
Thank you.
May I start? Do you hear me?
Yes, you can start, maybe.
Okay. Hi, everyone.
We can't hear too much. Can you speak louder?
Yes, sure. Now, is it better? Hello.
Try again.
Hi, hi.
So I guess the volume is a little bit low, Melih.
Can speak loud, maybe.
Şu an iyi mi? Tamam.
Can hear right now?
Şu an iyi mi? Şu an daha iyi mi? Bir saniye.
Daha sesli konuşman gerekecek.
Şu an iyi alabiliyor musunuz sesimi?
İyi.
Tamam, başlıyorum o zaman.
Oh, okay, you can start.
Okay. Today we will talk about first Ragers-Ramanujan identity. First, I will define what is an integer partition and some important theorems, and I will state Rogers-Ramanujan identity, and we have an idea that can help to find the bijective proof for Rogers-Ramanujan identity. Let's start. What's an integer partition? Integer partition of a positive integer n is a sequence of positive integers, lambda 1, lambda 2, blah blah, lambda k, such that their sum is n. And we will denote number of all partitions of n with key n. For example, for n equals 5, what is the number of all partitions? We can write 5 as just 5, or 4 plus 1, or 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, and just 1. Their number is 7, so P5 is 7. If we have some condition on partitions, we can write Pn such that the condition. This is the notation. And difference, we will use di in order to denote lambda I minus lambda I plus 1. And we can represent partitions by diagrams. The most popular one is Young diagram. For a partition, for example, lambda is 5, 4, 1. We will use squares, and every row contains lambda 1 or lambda 1, lambda 2, lambda 3 squares. There's a conjugation operation on Young tables. We can take symmetry as y equals minus x. You can think it's taking symmetry according to y equals minus x line. The conjugation operation is changing the partition, but it's the sum is still same. We will use conjugation operation to prove a theorem. I will show that. The theorem 2.2. The number of partitions of n such that parts are smaller or equal to k is equal to partitions of n such that number of parts smaller or equal to k. Think about the conjugation operation. Take a partition from left-hand side and take conjugate, and you will get another partition from left-hand side. Theorem 2.2 will be proved by conjugation of Young tables. Sequence model, we can represent partitions by sequence model, infinite sequence of natural numbers. For example, we have a partition. We will think about how many times we use numbers. F1 will be the number of repeating of 1. F2 is number of repeating of 2, etc. So all partitions can be represented by an infinite sequence. Two distinct partitions means parts are differing by at least 2. Okay, let's continue. Some important theorems. Euler theorem, theorem 2.1, is the most important theorem in integer partitions, I guess, and most popular one. Number of partitions of n such that parts are odd numbers is equal to number of partitions of n such that parts are different. Proof is based on this idea. Take a partition that satisfies left-hand side. Parts are odd. No, right-hand side. Take a partition that satisfies the condition in right-hand side. Parts are different. Look at the parts, and if it's odd, if it's even, just divide it into 2 parts. For example, one part is 4. Delete 4 and write 2 plus 2. All even parts will be divided into 2 parts and continue to this process, and you will get finally an odd partition. From right-hand side to left-hand side, we will use this. And from left-hand side to right-hand side, if you have repeated parts, for example, there is 2, 3, delete 3 and write 6. And continue to this process until there is no repeated part. Okay, let's continue. Yes. First Rogers-Ramanujan Identity. Efendim? Sesim iyi geliyor değil mi?
Geliyor, evet.
Devam ediyorum. First Rogers-Ramanujan identity is this for all positive integer n, number of partitions of n such that 2 distinct partitions is equal to number of partitions of n such that parts are congruent to minus or plus 1 modulo 5. This is also a very famous theorem, and there is no any simple proof. There's a few proofs. There are a few proofs, but they are very advanced, and some mathematicians tried to find a bijective proof for this theorem, and we tried also, but it seems very hard. But we have an idea to help find a bijective proof. Let's continue. Theorem 3.2, for all positive integer n, just observe the left-hand side is a extra condition of the Rogers-Ramanujan identity's left-hand side. This is two distinct partitions. There's two distinct partitions in left-hand side here. This is two distinct partitions, but just one part or D1 is greater than 2. The condition is that. And on the right-hand side, minus or plus 1 modulo 5, but there's an extra condition. It's f1 is greater than 0. So it means you has to use at least one. There's an at least one part, which is 1. We can prove this theorem by using Ragers-Ramanujan identity, and the corollary is number of partitions of n, which is 2 distinct, and d1 is 2. Now k is 1, just one part, or d1 is greater than 2. What is remaining? We had two distinct parts. We had two distinct partitions. Now 2 distinct, and k is equal to 1, or d1 is greater than 2. Now d1 is 2 on the left-hand side, and on the right-hand side we have f1 is 0. So in order to prove Ragers-Ramanujan identity, maybe we can find a bijection between two distinct, and D1 is 2 partitions, and minus or plus 1 modulo 5, and F1 is 0 partitions. If we can show corollary 3.3 without using Ragers-Ramanujan identity, then we can prove Ragers-Ramanujan identity. This is stronger version. It says number of partitions of n, which is 2 distinct, and lambda 1 is m. Well, lambda 1 is equal to m equal to n, or d1 is m plus 2. Just choose a natural number m, and this equation holds. 2 distinct partitions, and lambda 1 is equal to m, which is equal to n, or d1 is m plus 2, equal to number of partitions of n. Parts are equal to plus or minus 1 modulo 5, and f1 is m. What does it say? I will explain. For example, okay, let's say m is equal to 3. However you choose n, the number of partitions of n such that parts are plus or minus modulo 5, and you use 3 times 1 are equal to d1 is equal to 5. So in order to find the bijection, maybe we can match by using this statistics. The number of 1 we use in the right-hand side, and number of and d1. There is a relation between d1 on the left-hand side and f1 on the right-hand side. Yeah, that's all. Thank you for your listening.